Exploratory data analysis or EDA is the foundation of a data science project. Before building models, EDA helps you understand your data's structure, quality, and patterns, revealing underlying data quality issues, feature relationships, distribution insights, and business context that guide smarter decisions throughout the entire workflow. By systematically exploring data quality, engineering meaningful features, and visualizing relationships across variable types, you can uncover hidden patterns and catch potential issues early, saving hours of debugging downstream and ensuring that any models you select and build are grounded in a solid understanding of the data. Firstly, know the basic statistics of the dataset by importing the core Python libraries for data manipulation and visualization, to get a high-level understanding of any dataset using functions like info and describe, to inspect data types, basic statistics, and overall structure. We then focus on detecting and quantifying missing values, turning raw counts into percentages and visualizing them to reveal which fields may need attention before deeper analysis. Building on these insights, we introduce feature engineering as a practical way to transform raw fields into more informative variables, for example turning complex fields into binary flags or extracting date fields into year and month. Apply data transformations to convert complex fields into cleaner numeric or categorical features, and decide whether to keep or drop for further analysis. The next step is categorize these variables into numeric and categorical groups so that each can be analyzed with appropriate techniques, setting up a reusable pipeline that leads naturally into the process of univariate and multivariate analysis. Univariate analysis examines and summarizes one variable at a time, focusing on its distribution, central tendency, and variability. To perform univariate analysis systematically across the entire dataset, we can use bar charts for categorical features and histograms for numerical features to inspect distributions on datasets. Then perform multivariate analysis to examine two or more features at the same time to find patterns, correlations, and relationships among them. For relationships between pairs of numerical variables, apply correlation matrices, visualized as heat maps, with Seaborn pair plots to reveal both linear and nonlinear patterns. For categorical relationships, build grouped bar charts using Seaborn count plot with hue, iterating over pairs of categorical variables. This reveals whether any feature contributes to significant differences in data distribution across groups. For categorical numerical relationships, box plots are useful to compare numeric distributions across categories and flag differences worth deeper statistical analysis. We can further enhance the EDA process of two numerical and one categorical features by using pair plots with categorical variables as hue, making it easier to visualize any potential clusters formed in the numeric feature space. Let's recap. The EDA workflow begins with understanding the dataset's basic statistics, then moves to data manipulation and feature engineering, cleaning, transforming, and crafting informative features from the original data. Then perform univariate and multivariate analysis to uncover patterns and relationships. If you enjoyed this video, comment below with other data science topics you'd like to explore, and check out the full blog post linked in the description. After exploring our dataset thoroughly and identifying key patterns, we carefully select the most relevant features. This step ensures that we reduce noise and focus on the variables that truly impact our model performance. In the machine learning lifecycle, feature selection is a critical process that selects a subset of input features relevant to model training and prediction. Imagine training a model with hundreds of columns, but only a handful actually matter. The rest just add noise, cost, and confusion. That's where feature selection comes in. Instead of feeding every available column into the algorithm, we deliberately choose a smaller, smarter subset. We will start with uncovering 4 key reasons why feature selection matters. Firstly, as we add more and more features, the data space becomes sparse, and many algorithms start to struggle. This is often called the curse of dimensionality. Algorithms such as general linear models or decision trees can perform poorly when they have to learn patterns in very high-dimensional spaces. By selecting only the most useful features, we simplify the problem and make learning easier. Secondly, high-dimensional datasets are also expensive to work with. They require more memory, more processing time, and more experimentation to tune. When we reduce the number of features, we cut computational cost and complexity, which makes our workflows faster and more efficient. Additionally, too many irrelevant or redundant features can cause overfitting. The model starts memorizing noise in the training data instead of learning general patterns. Feature selection removes many of these distracting signals, so the model generalizes better to new, unseen data. Lastly, feature selection also makes models easier to explain. It's much simpler to justify predictions when they rely on a compact set of intuitive variables. Instead of scanning through dozens of columns, we can focus on a small group of features that clearly drive model behavior. Now that we understand why feature selection is important, we will dive into techniques and implementation using Python. One popular family of techniques is called filter methods. They score each feature based on how strongly it's related to the target variable, and then pick the top scoring ones. For classification problems, common scoring functions are chi-square, ANOVA, and mutual information. These scoring functions quantify the statistical relationship between each input feature and the target variable, assigning higher scores to features that show stronger associations and are therefore more likely to be useful for prediction. We can utilize the Python method SelectKBest from the scikit-learn library. There are two key parameters for this method: specify how many features we want to keep, and then train a model only on those selected features. To illustrate how it works, we use a credit card customer example to predict whether a customer is likely to churn, which is marked as the attrition flag in the example dataset. A logistic regression model is trained repeatedly using different numbers of selected features and different scoring functions. As more features are added, accuracy improves and then levels off, stabilizing at around 0.88 after roughly 8 features for most methods. Beyond that point, adding extra variables brings little or no gain. Next, we can visualize the feature importance score calculated based on different score functions. Different methods rank features slightly differently, but some variables consistently appear near the top. For instance, a feature like total revolving balance ranks among the top 3 across methods, matching earlier exploratory analysis. Another feature, card category, shows relatively high importance compared with other categorical variables. To validate these findings, we use exploratory data analysis to visualize the relationship between each feature and the target variable, attrition flag. We can see that these two features stand out in terms of their contribution to the variance between positive label and negative label groups. To sum up, feature selection is a critical step in machine learning workflow to mitigate the curse of dimensionality, reduce cost, prevent overfitting, while improve explainability. In practice, we can implement filter methods using scikit-learn SelectKBest method based on statistical function like ANOVA, and mutual information to determine which features should be selected for model training and prediction. Next, we move on to apply data transformations to these selected features. Data transformation is the process of converting raw data into a format that is easier for algorithms to learn from and for data scientists and data analysts to explore. It is a core part of feature engineering that helps reduce bias from skewed distributions. First, it makes features in the dataset comparable by putting them on similar scales and magnitudes, which helps models learn patterns more effectively. Secondly, it reduces skew and limits the impact of extreme outliers, which can otherwise bias your results. In this walkthrough, we'll use a marketing analytics dataset from Kaggle that contains customer demographics and purchase behaviors. We will demonstrate how to choose the appropriate data transformation technique according to the data properties. That includes domain-specific basic feature engineering. Apply log transformation for right skewed data. Clipping methods for handling outliers. We will also compare 3 data scaling techniques: MinMax scaler, standard scaler, robust scaler. For an article guide of these concepts and more details, please check out blog post with link in the description. Now let's start with simple feature engineering to make the data tidier and more meaningful using the pandas library in Python. First, we convert year of birth into an age feature by subtracting it from the current year. Then we turn the customer enrollment date into an enrollment_length feature by extracting the year and computing how long each person has been a customer. Next, we clean the income column. We remove currency symbols and commas, fill missing values with 0, convert the string to an integer, and then scale it down to millions of dollars as a new feature, income_$, which makes the distribution easier to visualize. Once we've engineered these basic features, we plot simple histograms for each numeric column. It quickly becomes clear that many variables are heavily right-skewed, and some, like age and number web visits month, contain extreme outliers. This is where transformation really matters. If we feed skewed and unscaled data directly into a model, it's more likely to become biased and misinterpret distances and relationships between points. For features that follow a power law pattern and have long right tails, we apply a log transformation using functions like np.log. In this dataset, most of the skewed variables fall into this category. After log transformation, the distributions become closer to normal distribution, which helps many algorithms that assume roughly Gaussian inputs. Next, we tackle outliers with clipping. We define upper and lower bounds using quantiles, typically from the 5th to the 95th percentile, and then cap all values outside this range. In practice, that means any values below the 5th percentile are raised to the lower bound and any values above the 95th percentile are reduced to the upper bound. For this dataset, clipping is particularly useful for age and number web visits month, which contain implausibly large values. This prevents a few extreme records from dominating the learning process. Once we've corrected skew and outliers, we scale the features so they share a comparable magnitude. For this, we rely on preprocessing tools, MinMax scaler, standard scaler, and robust scaler. MinMax scaler performs normalization, mapping each feature into a 0 to 1 range based on its minimum and maximum values. It's best used when the data isn't heavily distorted by outliers. Standard scaler does standardization, transforming features so they have mean 0 and variance 1 using the classic z-score formula. This is ideal when a feature is roughly normally distributed. Robust scaler is designed for skewed distributions and remaining outliers. Instead of mean and standard deviation, it uses the median and interquartile range, making it much less sensitive to extreme values. To compare these methods, we iterate through the numeric features, including those we clipped, and scale them using each of the 3 scalars in turn. The transformations don't change the shape of the distributions, but they do change the spread of the values. In this particular dataset, the key variables are neither severely distorted nor perfectly normal, so min-max scaling is a reasonable choice. Once all the transformations are applied, we plot the histograms again and compare them side by side. The before view shows heavily skewed, messy distributions. The after view looks more organized, with less distortion and more balanced ranges across features. This cleaner representation makes the data far more suitable for model training and for drawing insights through analytics and visualization. To recap, here's a quick checklist for numeric feature transformation. First, clean your data types and remove unnecessary characters in numeric fields. Second, apply log transformations to right-skewed features. Third, use clipping to rein in outliers based on sensible quantile thresholds. And finally, choose a scaling method that fits your data: min-max scaler for generally undistorted data, standard scaler for approximately normal distributions, and robust scaler when skew and outliers are still a concern. Thanks for reaching the end. Check out links in the description for more deep dives and related contents. Please like and subscribe if you'd like more videos like this.